Thank you very much for the invitation. I'm going to present work done with Fernando Martín Maroto. Fernando cannot be here. Fernando, maybe you are in Berlin. Hello, Fernando. He's in a meeting in Berlin. Let me put you in context what we want to do in this project. You know, probably most of you, the details of the mathematics of neural networks. In that case, you want to learn from data by doing error minimization, and you can include priors by choosing different architectures of your network. But you also know about good old symbolic AI, in which all items relate to the world and are handcrafted. They are not learned from data. In that case, you know that those systems are excellent for reasoning. They are very mathematically transparent. They are used today in proof assistance and expert systems, but they are limited in their contact with the world because they are not learning from data. So what we wanted is a bit the best of both worlds. We wanted a system that was mathematically very transparent, but could also learn from data. So I'm going to explain to you in 2 sentences what the whole project is about, and I will try to link it with neural networks and symbolic AI. There are 2 steps in what I'm going to explain to you. The first step is going to consist in using a formal language to embed data and prior knowledge as symbols in an algebra. I know there is a lot to unpack in that sentence. We will be unpacking that sentence later. The second step is going to be learning a specific model of this algebra using some internal symbols. Again, lots to unpack there, but we can see already a few things. One is that it is similar to neural networks in the sense that we are going to learn from data. However, it's very different to neural networks because we are not going to use a fixed architecture. We are not going to use optimization. We are not going to use error minimization, neither as a concept nor as a mathematics. It's similar to symbolic AI because we are going to put everything at the beginning into symbols that relate to things in the world. But it's going to be different to symbolic AI because the system is going to create also some internal symbols that do not relate to the world. Okay, so it has similarity with both approaches, but also differences. Now, the mathematics I'm going to use in the following are not standard. They are not studied in physics or engineering. They are fairly common for mathematicians. It's called abstract algebra, universal algebra, model theory. I'm not a mathematician myself, so I know where you are going to be in the next few slides. I will try to do it in a tutorial style. I cannot tell you everything. I hope you get a glimpse of how it works. So I will go more or less like a tutorial. First, if I'm going to unpack the 2 phrases I was telling you before, the first phrase was, uses a formal language to encode data and prior knowledge as symbols into an algebra. First, I need to tell you what my formal language is going to be. It's not going to be a complicated language. It's going to be a single operation symbol, okay? A circle with a little dot. It could be a Mickey Mouse at this point, and some constants. And the constants are going to be symbols that we use to refer to things in the world or abstract concepts that we might have. The way we use it is in an example in this way. Imagine that you have a 2x2 black and white image and a label. So the way we use constants is we create some objects and symbols, C11B to C22W, to refer to the pixels in the image. The 1,1 position in the matrix in black, 1,1 in white, and the 8 possibilities. Pictorially, because I'm going to use mostly images, you can refer as a symbol to the first pixel in black in this way, first pixel in white in this way, and the 8 possibilities, and P for the label. We can then express this image as gluing with the symbol these 4 constants, okay? And you can also create another term that refers to the label. Okay, so this is the part of the formal language. Constants that we can use it as symbols with letters and numbers, as pictures, and we glue those constants with the operation symbol. Now, what does the operation symbol mean? Here, nothing. It's just a picture. But in the next slide, I'm going to tell you what it really means. So I need to give some properties to the operation. You are used to sums, multiplications, and you think that they are very simple. This is actually simpler, but it looks complicated. It has 3 properties that are common to sums and multiplications, the commutative and associative properties. And idempotent one, maybe is the more different one. It's just that x operated with x gives x back. So the reason why we chose this operation is that is simple enough to derive theorems. So the whole thing of this approach is to be able to derive theorems about learning and still expressive enough to do machine learning. We are also thinking of adding new operations, but for today, we will have a single operation. That's my formal language. That's it. An operation symbol with its properties and the existence of constants. So we glue the constants to express things. I said, use this formal language to embed data. So how do we do that? Let's do it with an example. Let's say that our first training example is the image I showed before, and let's say that it has label P. So the idea is to say that, OK, if the image has property P, that means that if we operate property P with the image, it should give the image back, because it already has the property P. So formally, if we have the image before and the label P, if we operate P with the image, we have the image back, because P was already a property of the image. So the way we are going to express it is this result as a sentence is going to be in this way. That's how we say in this algebraic system that the image has label P. This notation is a bit cumbersome. I will tend to use another one that is a bit more intuitive, but it actually is notation. So I mean this by saying this thing here, that P is in the image. But in terms of my allowed operations, is this sentence here, OK? This is only notation. So I don't need to write so much. OK, so I also said that I can embed data and prior knowledge with the formal language. So how do I do it? So there are many types of prior knowledge you can include in the system. And all of them, I'm going to use simply the operation that some term is inside another one. Let's say, for example, that you have, for a given pixel in my image, 5 different, oh, this is very white, 5 different values. And these are not random values. They seem to be ordered. So I want to express to my system that they are indeed ordered. So that's what I do. I give a sentence to say that C5 is in C4, C4 in 3, 3 in 2, and 2 in 1, to express with sentences in my allowed formal language to express that these things are ordered. They're not just random values. OK, so that's how we express prior knowledge. I mean, of course, there are many other types of prior knowledge that can get much more complicated. But I also said in the second phrase that learning is going to be a specific model of this algebra using some internal symbols. So what are the internal symbols? So in my language, I'm going to have an extra type of constants that we're going to call the atoms, that are going to be created by the learning later, and I'm going to use Greek letters. It's going to have many properties, and I'm a bit lying here, but I'm going to tell you 2 properties. Each of these atoms is going to be in a constant, so we will write in Greek letters, and I tend to use phi, I don't know why. I would say that this atom is in this constant, OK? Now, adding a bit more notation, I will tend to use an arrow instead of the symbol, because I will have many atoms in the constants, and it's very difficult to write that symbol, so I'm going to use arrows. but they only mean that the atom is in a constant. The second property is that I'm going to force in my system is that these atoms are going to mirror the knowledge I was telling you before that a term was in another term. In using atoms is going to mean that the atoms in one term are going to be a subset of the atoms in the second term. Okay, I want to force these two properties for my atoms. And I was telling you before, the creative part of my system is going to be in building atoms. Okay, so what do we have? In the second phrase, I said, learning is going to be a specific model of the algebra using some internal symbols. I need to explain to you what model is, and also really what algebra is. So algebra is going to be this list. So we've been creating with our formal language 3 sentences to describe our operation. Then we might have n images for which we say that the label P is in this set of images. So there are n of those sentences. We might have also prior knowledge sentences and sentences for our atoms. This is my algebra, okay? So what is a model? A model is a particular mathematical structure in which these sentences are valid, are true. Okay, that's the definition of model. It turns out that there are many, many models, okay? And the reason why there are many models is that I'm asking of them only to obey the training data set. Outside this set T, they can behave in very different ways. You can have a model that says that some image has the label P and some other model that disagrees. It says, no, 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 it doesn't. So there will be many models agreeing or disagreeing on which images outside the training data set are in the class P or not. I don't know how to pick one, okay? We are not interested in general in any model. We are interested in models that can generalize, okay? Do I know how to pick it? No, I don't. So what can I do? I'm going to pick what I'm going to call the freest model. The freest model, like all these models, they need to obey, of course, the training data set. But it's going to be a particular model that says that no other image outside my training data set T will have P as label. It's a model that insists, okay, this image is in P because you told me in the training data set, P, P, P. But once you are done with the training data set, it will say no, 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 no to everything. Okay? It will insist that you only told to the system the training data set, and everything else will say, no, it doesn't have the property P. Now, you are going to tell me, well, that's not going to be a very good generalizing model. No, it's not. But it's one step in the way. I'm going to tell you one interesting property that gets us closer to a generalizing model. It's this theorem. So one can prove many things about the freest model. This is probably the more interesting one. I'm putting several theorems together here. When I say theorem, it's not how a mathematician reads a theorem. It's an informal way of telling you the theorem. And it says, the freest model can always be computed. I can always compute it. And if there is a rule in the data, the freest model is guaranteed to find it given enough data. Not guaranteed to be able to represent it, but to really find it, okay? So I need to do 2 things. One is to show to you how it is computed with an example, and I want to illustrate the theorem, that it's really true that it finds the rule in the data. So let's go for it. Let's imagine that we want to say to the system that P is a label in a given image. It's going to be the image we've been playing with all the time. Our initial model is one in which P will not be in any image. So no image will have P in the image. And we go through this procedure. There is a theorem that will tell you that This procedure that we call full crossing gives you the freest model. And what is the procedure? You take the atoms in the image. Okay, that's the image. So if it has this constant, what is the atom? Phi 1, okay, Phi 1. This other constant, where is it? Phi 5. This other constant, where is it? Phi 4 and Phi 8. You also take the atoms in P that are not in the image. The atoms in P that are in the image are all the atoms in P, Phi P. And then you fill the matrix with new atoms. And each of them is going to be in the constants that this one is, and also in the constants of that one. So P1, P4, P5, and P8. Let me plot them. For example, P1. P1 is in this constant, but it's also in P. Then I delete phi P, and I add these 4 new atoms. That, according to this theorem, gives you the freest model, the one that will say no, no, no to any new image. No one will be with label P. There are some atoms that are redundant in the sense that I don't need them, and there is an algebraic procedure to eliminate them because you see that there are others that are smaller that are doing the same job for any possible image, so you can eliminate them. They are irrelevant. And then you don't need to eliminate them, but you can eliminate them. I do eliminate them. And then you repeat the same procedure for all the training images, and you will obtain the freest model of the whole training data set. Note that I've never used any optimization. It's only set theoretic operations. Never I use optimization. OK, let's do an example. We are going to train that P is in this image, and all these images, and 14,911 ones, which consist in images that have one or more full black vertical bars. So that's a black vertical bar. This one has 2, 1, 2, 1, 2, 1, 2. And the rest of the pixels are randomly in white or black. So the rule is that it has black vertical bars, but the algebra doesn't know, so it needs to find it, okay? Let's see if it can do it. Let's first plot the many times I need to do a full crossing, that matrix I was showing to you before. There were 14,911 examples, and the number of non-redundant atoms shoots up to 50,000, and then it goes down to only 304. The theorem, if you remember, was saying that it should find the rule only in the limit of a large data set, so it should be here, okay? In these 304 atoms. So let's look at the atoms. I'm going to plot the same thing. This is the 14,911 examples. And now instead of the number of atoms, I write here the atom size. So these are the number of atoms of size 1, which is they are in 1 constant. Size 3, they are in 3 constants. Size 5, they are in 5 constants, and these are in more constants. Okay, so what happens in the limit of large data sets? I can promise to you that these disappear at the end, disappear, they disappear, disappear. You don't see it very well, but I promise to you that all those disappear. So the rule must be somewhere here. Let's look at them. The atoms here, and I plot them as a little gray square with the constant, are each of them in a single constant. There are 32 of those. This is the initial model. None of the atoms are in P. These are completely irrelevant. This is the initial model we started with. So let's look at the atoms of size 3. These are in P. These are the interesting ones. But each of them is in a white, black pixel in the same position in the image. So these atoms are in all images, okay? So all they are finding is that, Gonzalo, you were showing me images, okay? It knows that with those 16 atoms. So that's something, but it's not the rule. But these 256 atoms are more interesting. They are in P, and each of them is in 4 other black constants, 1 per column. And because it's 1 per column, it's 4 by 4 by 4 by 4, that is 256. Having all those 256 atoms, an image has, all those 256 atoms are in an image if the first one is in the image, the second one is in the image, so you can write them as an atom and the other constant. So each one needs to be in, so this one and this one and this one, so there are 256 terms with an and one of these atoms is in an image if one of the constants is already in the image. So it's enough with this or this or this or that. So we can write that as, okay, that pixel there, the second pixel is that one with ors. So you have or, and 256 terms like that. Using the distributive law for ands and nots and ors, you can rewrite the 256 cases as only 4. So in the end is this and this and this and this, or this and this and this and this. So you realize it did find that it's either the first black vertical bar or the second or the third or the fourth. So the rule that the system found was, you are giving me, Gonzalo, after all these many images that are black and 4 by 4 black and white images with 1 or more black vertical bars. So it did find the rule. But it needed all the data, okay? So it's not useful for real machine learning examples, but it's a theorem that tells you that it will find the rule, given enough data. But it's actually something interesting in the plot. You can see that although the theorem talks about the limit, about what happens here, if you look at the atoms of size 5, they are very, very stable, okay? And these ones are not. They are changing all the time. So what we can do for small data sets is to insist that what's happening is that those atoms are the ones that have the rule. So the idea is going to be simply to extract from all the thousands of atoms the ones that are successful, stable during training. We don't need to wait for all of them. We just take the stable ones. So it's very easy here to say, okay, these are the stable ones. It's much more difficult here, okay? But that's going to be the idea. I don't have time to give to you all the details of the next thing, but let me tell you the basic idea. So that was the reasonable hypothesis, that we could extract the stable atoms. If you do a full-blown statistical model, assuming that training and test obey the same statistics, which is a standard assumption, you will see that the subset of atoms of the freest model that gives you low test error needs to obey 2 conditions. That the atoms are the stable ones in training, which was our hypothesis. Okay, we thought that was going to be the case. But something that maybe you didn't expect is that you should not include in the subset those with high probability of being in negative examples. And the reason is the following. It was sort of obvious by eye that these atoms are stable. But within this mess of changing atoms, there will be a subset that is not, that can be large, but small compared to all these ones, but still larger maybe than these ones, that are also stable. But they are much more likely to be negative examples than these ones. So you can use the negative examples to extract out these ones and keep these in. If you follow those requirements, you can obtain different models at different full crossings. So basically, I'm blowing up the very beginning of the training, and you can find that the test error goes down very quickly, and by 100 crossings and 100 examples, you get a very good generalizing model. The test error is getting very close to 0. And one nice thing about this system is that it can actually find the exact model. So by 200 examples around, there, it finds the exact model. Not even an approximation. The error goes to completely 0. It really finds the rule without needing to wait all the data set, instead of, as the theorem was promising, by 200 examples, it finds the exact rule. I explain things in this way. The real one that we do it is another algorithm that I don't have time to explain. We tend not to produce all these atoms. They can be in the billions for practical examples, so we try to avoid it, but the theorems that we have, most of them are for this simpler case. Okay, so does it work in practice? So I use the example of the black vertical bar. I mean, the students in my lab know that I've been years now with a black vertical bar, okay? It's amazing how much, and I still don't fully understand it. So, but the bad thing about the black vertical bar, I mean, the good thing is that you know exactly what the algebra should be finding, I mean, because you're putting in. It's an artificial example. But you need to then show in real examples that it works. We are checking some of them. So for example, in binary classification of handwritten digits, our system, I'm not giving all the details, with no prior knowledge, just the simple algebraic machine learning will give a test error of less than 0.5%. And if you use a similar network with no prior knowledge, like the multilayer perceptron, you find very similar test errors. Okay, so bear in mind that, of course, we are not using any optimization. We are not using any error optimization, okay? It's not there. It's all by theorems and statistical models, but we are not using any optimization procedure, and still the error is similar. We have some collaborators in Germany that work in the opportunity data set. The input to in this case, is sensor data to the network or to algebraic machine learning, and the output is human behavior, sitting, walking. And they found, we sent the software to them, that it worked better than the ones they tried. They didn't try many of them, but I guess the reasonable ones. For example, multilayer perceptron. In this case, actually, it's not like here. It was much better than the multilayer perceptron, but in all honesty, so what is it here, the honesty? Yes, the honesty is here. So we are using, in this case, that the prior knowledge that the sensor data is also ordered, which actually, I mean, we can discuss it. It's also implicit in the networks. Okay, so if we wanted to compare to other networks, and we are doing that job, what we need to do is for each of them to express to the algebras the prior knowledge. So if you wanted a CNN, or compared to a CNN, you need to understand how to express formally translational invariance or locality in a space, and add it, see what happens, and then compare, and we are in the way of doing it. Something I very quickly wanted to say is that the same algorithm, the same software, you just can tell it to do other things. We are telling the system, P is in this image, P is in this image, P is in this image, but we can tell to play games or to solve puzzles and everything. So for example, here we are asking the system with a set of sentences to solve the n queens problem. You need to place in a board of 8 by 8, 8 queens in non-attacking positions. So you express, for example, that each queen in position x, y needs to have some empty positions in diagonals, in the row and the column, and many other things. It's similar to explaining to your children, but with a formal system. And then it runs, and at some point it finds a solution. Here is non-unique. There is more than one solution, so it continues and it finds another solution, and it continues and it finds another solution. And it's the same algorithm. There's nothing that has changed. And I'm basically done. Just to summarize, we've been using a formal language to explain how the data is labeled, any prior knowledge we might have about the problem. And the first step was that. The second step was to obtain as a specific model, the freest model, that, for which we have a theorem that in the large data set case, if it has to find a rule, if there is one in the data. We obtained that model only with set operations. We were not using optimization. And we show by statistical modeling that the stable atoms of the freest model are the subset that is a generalizing model, and we never use, again, I'm hammering that we are not using optimization methods. Thank you very much.